This is the solution for problem number 5 from homework 1, sections G through H, which is based on number 12 from section 1G, and I'm just going to do the version from the manual. So this problem is a beast. It's pretty complicated. So we have some information about some transactions that are made within an account, deposits and withdrawals and that sort of thing. Before I get to that though, we're given this force of interest, and I want to use this to find our accumulation function. Okay, so before I integrate this force of interest, I'm going to rewrite it slightly. I'm just going to distribute the parentheses. I'm going to get rid of the parentheses in the denominator. So if I do that, that gets me k over 1 plus k minus kt. So now when I plug this into the integral from 0 to t delta r dr, that's going to give me 0 to t k over 1 plus k minus kr dr. So the first thing to notice is that our standard shortcut for these integrals does apply here, sort of. The denominator in the derivative of the denominator would be minus k, and my numerator is plus k. So I'm off by a sign. So what I'm going to do here is I'm going to multiply the inside of the integral by -1, and to balance things out, I'm also going to multiply the outside of the integral by -1. So now my numerator is the derivative of the denominator, and when I integrate, I'm going to get minus natural log of just the denominator, 1 plus k minus kr. You don't have to use the shortcut on this. There are other ways of doing this integral, but since I think we all kind of know this shortcut, so we'll stick with that. That's the easiest way. Okay, so then if whenever I have a negative like this in front of my integrand, or in front of my antiderivative, I like to swap the orders of my limits of integration to get rid of the negative sign. It just makes it less likely for me that I'm going to make a sign error. So I'm going to get the natural log of 1 plus k minus kr, evaluated not from 0 to t, but from t to 0. Okay, so now I plug in my limits of integration, and I get the natural log. When I plug in 0, I get the natural log of 1 plus k. Minus, when I plug in t, I get the natural log of 1 plus k minus kt. Okay, so that was all a little bit of a mess. So my accumulation function now is a of t equals e raised to the ln of 1 plus k minus ln of 1 plus k minus kt, and I can use the laws of logarithms to write that as, let me fix that, as e to the ln 1 plus k divided by e to the ln 1 plus k minus kt. And so, of course, this all simplifies at the end of the day to 1 plus k over 1 plus k minus kt. That is my accumulation function. Okay, so let me highlight that so that I can reference back to it later. Okay, so now let's look at the details for this specific account. Okay, so we are told at time 0, our account has $100 in it. $100,000 in it. But in fact, just to make the number simpler here, I'm going to write this as 100. And then at time 1, the balance of our account is $110,000. So I'm going to write that as 110. And then throughout the course of the year, there are two transactions. One occurs at time 0.25, the other occurs at time 0.75. At t equals 1/4, there's a deposit of 15, and at t equals 0.75, there's a withdrawal of 20. Okay, so it's really 15,000 and 20,000, obviously. Okay, so what I'm going to do here, this balance at time 0, I'm just going to re-envision this as a deposit that was made at time 0. So you can kind of imagine here that I have three transactions that take place over the course of the year. A deposit at time 0, a deposit at time 15, and a withdrawal at time 0.75. And all told, those transactions should accumulate to $110. So my equation is going to be $100, my 100 deposit at time 0, accumulated forward from time 0 to time 1, plus my $15 deposit at time 0.25, accumulated from time 0.25 up to time 1. And then I have a withdrawal, so I'm going to put a negative sign here. And this is accumulated from time 0.75 to time 1. And if I take into account all of these transactions, my final balance should be 110. Okay? So I should calculate the value of my accumulation function at these specific numbers, a of 1, a of 0.25, and a of 0.75. I'm going to do that over here on the side, and this is pretty straightforward. You can just check my work on this, but a of 1 is actually equal to 1 plus k. A of 0.25 is 1 plus k divided by 1 plus 0.75k, and a of 0.75 is equal to 1 plus k divided by 1 plus 0.25k. Okay, so plugging into my equation here, 100 times A1 plus 15 times A1 divided by A of 0.25. So I'm going to do this. I'm going to do 15 times A of 1. Now if I'm dividing by A of 0.25, really I can just multiply by the reciprocal. So this is going to give me 1 plus 0.75k divided by 1 plus k minus 20 times a of 1, and then in a similar way I need to divide by a of 0.75, so I multiply by the reciprocal to get 1 plus 0.25k divided by 1 plus k equals 110. Okay, so obviously there's some simplification here I can do. And this leaves me with, let me rewrite that equation just in a little bit cleaner fashion. This problem is complicated, but fortunately we're almost done with it. Okay, it's kind of all algebra from here on out. So I get rid of my parentheses by distributing, and so I get 100 plus 100k plus 15 plus 11.25k minus 20 minus 5k equals 110. So I'm going to collect like terms. Let's see, where are my k's at? K, k, k. Bringing all those together, that's going to give me 106.25k. Putting all my constants together on the left-hand side, I get 95. So that's going to give me 106.25K equals 15, or K equals 0.14117, which is answer C. Okay, that's that. Long story short, hope that you don't get that problem on the FM exam.